The story of Wi-Fi is, at its core, a tale of invisible waves, ingenious invention, and the persistent human drive to connect. To understand how Wi-Fi became such an essential part of modern life, buzzing through our homes, schools, offices, and public spaces, it helps to trace both the scientific roots of wireless communication and the historical milestones that shaped its evolution. It all begins with the physics of electromagnetic waves. Wi-Fi, like all wireless technology, relies on energy traveling through space as oscillating electric and magnetic fields. These electromagnetic waves span a broad spectrum of frequencies, from radio waves at the low end through microwaves, infrared, visible light, ultraviolet, and beyond. For wireless communication, the relevant portion is the radio spectrum, ranging from about 3 kHz up to 300 GHz. Imagine tossing a pebble into a pond and watching the ripples spread out. Radio waves behave in a similar way, rippling invisibly through the air and carrying information from point to point. A key feature of radio waves is their ability to be modulated. Modulation is the process by which information, whether it is a human voice, a song, or computer data, is encoded onto a carrier wave for transmission. Early radio technologies used amplitude modulation, where the strength of the wave is varied, and frequency modulation, where the frequency is altered. As digital communication advanced, more sophisticated schemes emerged, such as phase shift keying and quadrature amplitude modulation. Both are used in Wi-Fi technology to efficiently encode and transmit bits of data. But the existence of radio waves is only the physics. The story of Wi-Fi is also one of people and technological leaps. The earliest visionaries of wireless communication include Nikola Tesla, who experimented with radio waves as early as the late 19th century, and Guglielmo Marconi, whose work in wireless telegraphy helped establish radio as a practical tool for communication across distances. Each contributed to the foundation upon which all wireless technology rests. A particularly pivotal chapter unfolded during World War II, when Hedy Lamarr, a Hollywood actress with a keen technical mind, and composer George Antheil devised a method called frequency hopping spread spectrum. Their invention was intended to guide torpedoes securely by rapidly changing the radio frequencies used for communication, making it nearly impossible for enemies to jam or intercept signals. Although it was not widely adopted at the time, the principle of spreading a signal across multiple frequencies for security and reliability would prove essential decades later, forming part of the backbone of modern wireless networking, including Wi-Fi. As the decades passed, the world grew increasingly networked, and the appetite for connectivity expanded far beyond telegraphs and radios. The 1970s marked a turning point. In 1971, researchers at the University of Hawaii demonstrated hallucinate, one of the first systems to use radio waves for computer networking. Hallucinate's success proved that it was possible to transmit data wirelessly, laying crucial groundwork for what would come next. Around the same time, Bob Metcalfe and David Boggs developed Ethernet, a wired networking technology that would later influence wireless networking standards by providing a model for how devices could efficiently share a network. A significant regulatory milestone arrived in 1985, when the United States Federal Communications Commission opened sections of the radio spectrum known as the ISM bands, short for industrial, scientific, and medical, for unlicensed use. This decision allowed innovators to experiment freely with wireless technologies in the 2.4 GHz and 5 GHz bands without the costly and time-consuming process of acquiring a license. The ISM bands became the playground for a new generation of wireless technologies and, as history would bear out, the cradle of Wi-Fi. In the late 1980s, companies began to explore the practicalities of wireless local area networking. By 1988 and 1989, products like Wavelan appeared, offering commercial wireless networking within limited spaces like offices and campuses. These early systems were far from perfect. Speed was limited, reliability was challenging, and interference from other devices in the unlicensed bands was a constant concern. Yet, they demonstrated the tantalizing potential of untethered connectivity. A persistent technical challenge faced by early wireless networks was the phenomenon of reverberation radio signals bouncing off walls and objects, causing multiple versions of the same signal to arrive at a receiver at slightly different times. This could scramble the data and make communication unreliable. In the 1990s, researchers at Australia's CSIRO radiophysics laboratory tackled this problem head-on. By transmitting multiple signals in parallel and employing advanced error correction techniques, they found ways to extract the correct data from the chaotic jumble of reflected signals. Their innovations contributed directly to the creation of robust wireless local area network, WLAN, technology, making Wi-Fi practical in real-world environments. Momentum was building. In 1990, a formal effort to standardize wireless networking began with the creation of the IEEE 802.11 Working Group. Vic Hayes, sometimes called the father of Wi-Fi, led the group in developing a set of protocols and technical specifications that would allow computers and devices made by different manufacturers to communicate seamlessly over wireless networks. These standards, published under the IEEE 802.11 banner, specify both the physical, PHY, and media access control, MAC, layers that define how Wi-Fi operates. The architecture of a Wi-Fi network, as outlined by the IEEE standards, centers on two types of devices: stations, such as laptops, smartphones, and tablets, and access points. Access points act as the bridge between the wireless and wired world, connecting wireless stations to a local network and, often, to the internet. This architecture allows for great flexibility. Access points can be placed wherever coverage is needed, and clients can move freely within range. The choice of frequency bands has always played a major role in Wi-Fi's capabilities. The 2.4 GHz band, one of the ISMM bands, offers long range and good penetration through walls, but it is relatively crowded and subject to interference from other devices like microwave ovens and cordless phones. The 5 GHz band, also unlicensed and widely adopted in later Wi-Fi standards, provides higher speeds and more available channels, but its signals do not travel as far or through obstacles as easily. The analogy often used is that the 2.4 GHz band is like a wide, busy highway, plenty of space, but lots of traffic, while the 5 GHz band is like a faster, less congested expressway, ideal for quick trips but with a shorter reach. More recently, the 6 GHz band has been added to the Wi-Fi family, offering even more speed and capacity, though with an even shorter range. The IEEE 802.11 standard, first published in 1997, marked the formal birth of Wi-Fi as a technology. It allowed for wireless connections at speeds up to 2 megabits per second in the 2.4 GHz band. While modest by today's standards, this was a significant leap. The years that followed saw rapid evolution. 802.11a, introduced in 1999, brought speeds up to 54 megabits per second in the 5 GHz band. 802.11b, also in 1999, offered 11 megabits per second in the 2.4 GHz band, making Wi-Fi more affordable and accessible to consumers. These advances paved the way for mainstream adoption. A watershed moment arrived in 1999 when Apple released its airport wireless networking products alongside the iBook laptop, among the first consumer devices with built-in Wi-Fi capability. This move showcased Wi-Fi's potential to the public and signaled the beginning of its widespread adoption. From that point, the IEEE 802.11 standards continued to evolve. 802.11g in 2003, 802.11 and in 2009 with multiple input, multiple output MIMO technology for greater throughput and reliability. 802.11ac, Wi-Fi 5 in 2014, focusing on the 5 GHz band, and 802.11ax, Wi-Fi 6 in 2019, bringing even higher speeds, improved efficiency, and greater capacity in crowded environments. The latest standard, 802.11be, also known as Wi-Fi 7, is set to continue this trajectory. To ensure that Wi-Fi devices from different manufacturers could work together seamlessly, the Wi-Fi Alliance was formed. This industry group established certification programs leading to the familiar Wi-Fi certified CLM products. While Wi-Fi itself is a brand name, not an acronym, it has become synonymous with wireless local area networking, and the Alliance's efforts have ensured interoperability and fueled the explosive growth of Wi-Fi-enabled devices. Behind the scenes, the scientific principles that enable Wi-Fi are grounded in the physics of radio frequency communication. When a device transmits data over Wi-Fi, it converts digital information into electromagnetic waves using modulation schemes like PSK and QAM. These signals propagate outward from the antenna, and their journey is shaped by the environment. As they move, they can be absorbed by walls, reflected off surfaces, scattered by objects, refracted as they pass through different materials, and even diffracted around corners. The behavior of these waves is governed by the fundamental laws encapsulated in Maxwell's equations, a set of mathematical rules describing how electric and magnetic fields interact. The practical deployment of Wi-Fi networks requires thoughtful planning. Because the 2.4 GHz and 5 GHz bands are unlicensed and shared, careful selection of channels and frequency planning is necessary to avoid interference, especially in dense environments. Access points must be strategically placed and their antennas aligned to maximize coverage and minimize dead zones. The choice of frequency band can influence both the range and speed of the connection. Lower frequencies travel farther and penetrate walls better, while higher frequencies deliver faster data rates but are more easily blocked. Wi-Fi networks are built around a simple yet effective architecture. The access point serves as the central hub, broadcasting a network name or SSID, which devices use to identify and join the network. The access point manages communication, ensuring that data packets from each device are delivered to the right destination. In larger environments, multiple access points can be deployed to extend coverage and handle more users, all interconnected, often through wired links to a central router that manages the flow of data to and from the internet. As Wi-Fi matured, so did the ways it was used. Early networks were primarily deployed in offices, universities, and other institutional settings, but the advent of affordable access points and client devices soon brought Wi-Fi into homes, cafes, airports, and virtually anywhere people gathered. The concept of public hotspots, places where anyone could connect wirelessly to the internet, emerged and spread quickly, further cementing Wi-Fi's role as a pillar of modern communication. Throughout its development, Wi-Fi has remained true to its origins, a family of wireless networking protocols, based on the IEEE 802.11 standards, operating in globally agreed-upon unlicensed frequency bands, and designed for interoperability and accessibility. Its evolution has been shaped by advances in both science and engineering, as well as by regulatory decisions and the vision of countless inventors and researchers. Today, Wi-Fi is the world's most widely used wireless networking technology, enabling local area networking and internet access in homes, businesses, and public spaces everywhere. Its success is the result of decades of scientific inquiry, bold experimentation, and the steady refinement of both the invisible waves that carry our data and the standards that make them work together. As new standards continue to emerge and new applications are imagined, Wi-Fi stands as a testament to the enduring power of wireless connectivity, a bridge across space, built on the foundations of science, collaboration, and the simple human desire to connect. Imagine opening your laptop or unlocking your phone, watching those familiar bars fill with white, and knowing almost instinctively that you are connected. But what unseen choreography brings your message, movie, or video call across the room, through the walls, and out into the world? The answer lies in the intricate workings of Wi-Fi technology, a marvel of engineering that makes the invisible visible and the distant suddenly near. At the heart of every Wi-Fi connection is a conversation between your device and an access point, often built into a wireless router. While routers and access points are sometimes used interchangeably in marketing, they serve distinct roles in a network. The router's main job is to direct traffic between your local network and the broader internet, managing data paths and ensuring each packet of information reaches its destination. The access point, on the other hand, acts as the wireless gateway, linking devices, laptops, phones, tablets, even smart refrigerators to the wired network. In modern homes and offices, routers often double as access points, but not the other way around. An access point alone cannot handle routing duties. When you connect to Wi-Fi, your device is known as a station, and together with the access point, it forms the backbone of the local wireless network. Each access point broadcasts a unique network name, called a service set identifier, which your device scans for when searching for available networks. Once you select and join a network, the access point and your device exchange digital handshakes, packaging data into packets for efficient transmission over the air. Behind the scenes, this communication is governed by a set of rules and protocols defined by the Institute of Electrical and Electronics Engineers 802.11 family of standards. At the core of these standards are two key layers, the Media Access Control, or MAC, layer, and the Physical, or PHY, layer. The Media Access Control layer decides when and how data is sent, ensuring only one device transmits at a time to prevent chaos on the airwaves. It uses a system called carrier sense, multiple access, with collision avoidance, or CSMA, Before transmitting, a device listens to the radio channel to check if it is clear. If the air is busy, the device waits for a random period, an elegant way to minimize the chance of two devices transmitting simultaneously and garbling their messages. The Physical, or PHY, layer handles the mechanics of moving data through the air. It determines how radio signals are modulated, how fast data can be sent, and how sensitive the receiver must be to pick up faint transmissions. Each new version of the 802.11 standard, Whether it is the older 802.11b or the cutting-edge 802.11be, introduces new capabilities at both the media access control and physical layers, often boosting speed, reliability, or efficiency. A central challenge for Wi-Fi engineers has been ensuring that each new standard remains compatible with older devices and networks. Backward compatibility allows a brand new phone to connect to a 10-year-old access point, even if it cannot achieve the latest blazing fast speeds. This coexistence is carefully managed so that networks with mixed generations of devices continue to function smoothly. The physical world in which Wi-Fi operates is rarely orderly. Radio waves travel through the air, but they also bounce off walls, are absorbed by furniture, and get tangled with signals from other devices. To maximize performance, the placement of access points and routers is critical. Positioning a router centrally in a home or office, with antennas properly aligned, can mean the difference between seamless streaming and constant frustration. Overlapping frequencies from other wireless networks or even from household devices like microwave ovens and cordless phones can degrade performance, leading to dropped connections and slower speeds. The airwaves Wi-Fi uses are divided into bands and channels. Most people are familiar with the 2.4 GHz and 5 GHz bands, but newer standards have begun tapping into the 6 GHz range as well. Within each band are channels. Think of these as lanes on a highway. Choosing the right channel is crucial, especially in crowded neighborhoods or apartment buildings where many networks compete for the same space. When too many networks use the same channel, interference increases, slowing data for everyone. Not all channels are created equal, and not all are available in every country. Some channels overlap, causing interference even when networks are technically on different channels. This is especially problematic in the 2.4 GHz band, which is crowded not only with Wi-Fi networks, but also with non-Wi-Fi devices that use the same slice of spectrum. Microwave ovens, Bluetooth gadgets, some baby monitors, and even wireless game controllers can all disrupt Wi-Fi signals. Careful channel planning, choosing non-overlapping channels, and positioning access points to minimize interference can help, but there are limits to what can be achieved in densely populated areas. To combat congestion and boost speeds, newer standards have introduced techniques like channel bonding, which combines two or more channels into a single, wider channel. This allows more data to be sent at once, much like adding extra lanes to a highway. However, using wider channels also increases the risk of interference, especially in the already crowded 2.4 GHz band. The 5 and 6 GHz bands offer more channels and wider spacing, making channel bonding more practical and effective. The technical details of each Wi-Fi standard can seem overwhelming. Consider the differences between the most common standards in use today. 802.11ac, also known as Wi-Fi 5, operates primarily in the 5 GHz band and supports channel widths up to 160 MHz, enabling higher speeds and less interference. 802.11ax, or Wi-Fi 6, builds on these improvements with features designed for dense environments, such as apartment buildings or stadiums where many devices compete for airtime. Wi-Fi 6 introduces technologies like orthogonal frequency division, multiple access, which subdivides channels so multiple devices can transmit at once, and multi-user MIMO, which allows an access point to communicate with several devices simultaneously. These innovations increase efficiency and capacity, ensuring that even as our homes fill with more gadgets, performance remains strong. Another advancement, BSS coloring, tags transmissions from different networks, helping devices ignore irrelevant signals and further reducing interference. The leap to Wi-Fi 7, or 802.11be, promises even more dramatic improvements. With support for channel widths up to 320 MHz and advanced modulation schemes like 4096 QAM, Wi-Fi 7 can, in theory, reach data rates up to 40 gigabits per second. This is significantly faster than earlier generations. Wi-Fi 7 also introduces multi-link operation, allowing devices to use multiple bands and channels simultaneously, reducing latency and improving reliability. These features make Wi-Fi 7 especially well-suited for applications requiring ultra-high speeds and minimal delays, such as virtual reality or cloud gaming. Yet, the impressive numbers on spec sheets only tell part of the story. Real-world performance depends on many variables: signal strength, interference, the number of connected devices, and even the materials used in your walls and furniture. Dense walls, metal appliances, and even fish tanks can absorb or reflect Wi-Fi signals, degrading connectivity. Solutions like mesh networks, where multiple access points work together to blanket a space with coverage, can help overcome these obstacles. Range extenders can also boost signal strength in hard-to-reach corners, though they may introduce their own limitations, such as reduced throughput. As Wi-Fi networks have grown more complex and essential, security has become paramount. The earliest security protocol, WEP, introduced in 1997, was quickly found to be vulnerable. Its successor, WPA, arrived in 2004 and introduced stronger encryption. WPA-2, also released in 2004, brought further improvements and became the standard for over a decade. The most recent advancement is WPA-3, ratified in 2018. WPA-3 uses robust encryption algorithms such as AES-GCM and introduces features like simultaneous authentication of equals, SAE, which makes passwords harder to crack. It also enables individualized data encryption, so even on open or public networks, each user's traffic is kept private from others on the same network. Enhanced open modes provide better security in cafes and airports, while improved protection against brute force attacks further strengthens the system. However, these benefits require both the router and connecting devices to support WPA3, so its adoption has been gradual. Encryption is not just a technical detail, it is what keeps your information safe as it travels over the air. Without it, anyone within range could intercept your emails, passwords, or financial data with relative ease. As more aspects of our lives move online, robust Wi-Fi security becomes not just a convenience, but a necessity. Performance is not solely about speed or security. The reliability of a Wi-Fi network depends on thoughtful setup and ongoing maintenance. Central placement of the router, regular firmware updates, and the use of quality of service (QoS) settings to prioritize important traffic like video calls over file downloads can all make a noticeable difference. Even simple steps like changing a crowded channel or upgrading outdated hardware can yield dramatic improvements. Troubleshooting Wi-Fi issues often requires detective work. Weak signals might be fixed by repositioning the router or adding extenders. Overlapping channels can be reconfigured to reduce interference. Unauthorized users can be blocked with stronger passwords and better encryption. Sometimes, the culprit is outdated firmware, which can be resolved with a quick update. Bandwidth hogging by streaming devices or large downloads can be managed with QoS, or by scheduling heavy usage during off-peak hours. The ecosystem of devices that operate in the same frequency bands complicates matters further. Beyond Wi-Fi, the 2.4 GHz and 5 GHz bands are shared by technologies like Bluetooth and Zigbee, as well as everyday appliances like microwave ovens. This competition for bandwidth can result in dropped connections or sluggish speeds, especially in environments dense with wireless signals. The expansion into the 6 GHz band with Wi-Fi 6E and Wi-Fi 7 is designed, in part, to alleviate this congestion, but only devices built to use these bands can take advantage. With each generation, Wi-Fi has become more sophisticated, integrating features that not only boost speed, but also enhance stability, security, and efficiency. Wi-Fi 6 and 6E introduced target wake time, which schedules when devices wake up to transmit data, saving battery life in everything from phones to smart thermostats. Spatial stream management, dynamic channel allocation, and even AI-driven optimization are finding their way into high-end routers, automatically diagnosing issues and fine-tuning settings for the best experience. Yet, despite all these technological leaps, the same essential dance continues: devices and access points, orchestrated by intricate protocols, negotiating for their turn to speak, cooperating to avoid collisions, and adapting to the messy, unpredictable realities of the physical world. Whether you are streaming a movie, joining a work meeting, or simply browsing the web on the couch, the seamlessness you experience is the result of countless innovations layered atop one another, each solving a different piece of the wireless puzzle. In the end, Wi-Fi is more than just a utility. It is an invisible infrastructure, as vital to modern life as electricity or running water. Its technology and protocols, though complex, exist to serve a simple goal: to connect us, wirelessly and effortlessly, to each other and to the world beyond our walls. Step into almost any home cafe, airport lounge, or city plaza, and you will find Wi-Fi as natural as the air itself. What began as a niche technology has become the silent engine of our digital lives, reshaping how we work, learn, socialize, and even govern. Today, Wi-Fi connects billions of devices worldwide, moving from the background to center stage in our daily routines. Its journey from the early days of specialized networking to a global utility reveals not just a story of technical evolution, but a sweeping societal transformation. Consider the modern household. A typical day might begin with a smart alarm clock syncing overnight data, coffee brewed by a Wi-Fi-enabled machine, and children logging into online classrooms from their bedrooms. Parents may join video calls or access cloud documents from a sunlit kitchen table, while a doorbell camera keeps watch outside. This seamless digital choreography would be unimaginable without Wi-Fi, which now serves as the backbone of home connectivity. As of 2012, a quarter of households worldwide had already adopted Wi-Fi, and that number continues to climb. Wi-Fi is no longer just a convenience. It is a necessity, providing the foundation for remote work, streaming entertainment, and smart home automation. Step outside and Wi-Fi's influence grows even more apparent. In the business world, robust wireless networks are as essential as electricity. Retailers offer free Wi-Fi to attract customers and keep transactions running smoothly, while offices depend on secure, high-capacity networks to power everything from collaborative workspaces to video conferencing suites. In many urban centers, Wi-Fi coverage extends beyond office walls, reaching into lobbies, courtyards, and even parking lots. This connectivity is more than a perk, it is an expectation. For property developers, reliable Wi-Fi has become a selling point, increasing the value of homes and commercial spaces alike. Real estate professionals note that connectivity now ranks alongside water and heat in the minds of prospective buyers and tenants. Beyond the private sector, Wi-Fi has become a vital engine for economic growth and community engagement. City governments and local organizations deploy public Wi-Fi to bridge digital divides, offering free or low-cost access in libraries, parks, sports arenas, and transit hubs. The presence of public hotspots, numbering over 1 million globally by 2011 and now in the millions, enables residents and visitors to stay connected, whether navigating a new city, attending local festivals, or accessing essential services. In small towns and cities, public Wi-Fi is credited with revitalizing downtown districts, supporting local events, and enabling new forms of digital ticketing and civic participation. The expectation of universal connectivity has become so ingrained that a lack of Wi-Fi can be a barrier to tourism, business, and even basic communication. For communities, the benefits of public Wi-Fi go deeper than convenience. During emergencies, public networks can provide critical communication channels when other infrastructure is disrupted. Wi-Fi-enabled sensors and Internet of Things devices deliver real-time information to first responders, monitor environmental conditions, and help manage public health by tracking air quality or foot traffic. Educational outreach, digital literacy programs, and remote work initiatives all benefit from safe, accessible public Wi-Fi, enabling broader participation in the digital economy. As more devices and services rely on connectivity, Wi-Fi's role in social inclusion and economic opportunity continues to grow. The economic impact of Wi-Fi is staggering. In the United States alone, its annual value is projected to reach $2.4 trillion by 2027. Globally, the figure is set to approach $5 trillion by 2025. These numbers reflect not only the direct revenues from Wi-Fi-enabled devices and services, but also the vast productivity gains in sectors like telehealth, logistics, education, and smart city management. Spectrum policy, such as the allocation of additional 6 GHz and 7 GHz frequencies, will be a major driver of future growth, unlocking new applications and supporting ever-increasing demand. The ripple effect touches nearly every aspect of modern life, from the convenience of grocery delivery apps to the efficiency of connected factories and the democratization of information access. At the same time, Wi-Fi has contributed positively to environmental sustainability. Devices built on newer standards, such as Wi-Fi 6, can consume up to 67% less power than their predecessors. This efficiency is crucial as billions of devices, phones, tablets, thermostats, cameras, and countless IoT gadgets connect to global networks. The reduction in energy use not only lowers operating costs but also reduces the environmental footprint of our increasingly digital lives. Yet, as transformative as Wi-Fi has been, it is not without challenges. Chief among these is interference. As more devices crowd the airwaves, especially in densely populated neighborhoods and public spaces, signals can overlap and degrade. Competing access points, electronic appliances, and even neighboring networks can cause congestion, reducing speeds and reliability. While recent standards and better spectrum management have alleviated some of these issues, interference remains a persistent hurdle, particularly as Wi-Fi expands into high-density environments like stadiums, airports, and apartment complexes. Bandwidth limitations are another ongoing challenge. Demand for wireless data continues to climb, fueled by high-definition streaming, cloud gaming, telehealth consultations, and the proliferation of connected devices. Even with newer standards like Wi-Fi 7 promising theoretical speeds up to 46 gigabits per second, the reality often falls short due to physical barriers, crowded channels, and the limitations of existing infrastructure. Achieving the promise of ultra-high-speed broadband for all will require not just technical advances, but also smart deployment, thoughtful spectrum allocation, and ongoing investment in infrastructure. Security is perhaps the most visible and evolving concern. The very openness that makes Wi-Fi so accessible also exposes users to risks. Open networks in public places can be vulnerable to eavesdropping, data theft, and unauthorized access. While advances in encryption and authentication have made networks more secure, the sheer number of devices and access points creates a wide target for cyber threats. Businesses and individuals alike must remain vigilant, updating hardware, using strong passwords, and practicing good digital hygiene. As Wi-Fi becomes ever more embedded in critical infrastructure from hospitals to transportation, the stakes for security only increase. There are also questions about accessibility and digital equity. While Wi-Fi has democratized internet access for billions, gaps remain. Rural and underserved urban areas may lack robust coverage, limiting opportunities for remote work, online education, and access to essential services. Efforts to expand public and community Wi-Fi are helping to bridge these divides, but progress is uneven and dependent on local investment and policy priorities. On the societal front, the ubiquity of Wi-Fi has transformed communication and information access, enabling new forms of civic participation and digital literacy. Public spaces have taken on new roles as digital commons, where people gather not only to socialize but also to work, learn, and engage with their communities. Wi-Fi-enabled sensors and Internet of Things applications are helping cities become more resilient, responsive, and sustainable, supporting everything from efficient waste management to real-time transit information. The environmental benefits extend beyond device efficiency, as smarter connected systems can reduce energy consumption and optimize resource use across entire cities. With all these advances, questions about health and safety sometimes surface. Current scientific reviews of Wi-Fi technology and human exposure to electromagnetic fields have not found conclusive evidence of harm at the levels used by wireless networks. Still, research continues, and policymakers monitor developments to ensure public safety as new standards and applications emerge. Looking forward, the future of Wi-Fi is both promising and complex. Innovation shows no sign of slowing. Wi-Fi 7, also known as 802.11be, is poised to deliver dramatically higher speeds and lower latency, making it ideal for high-density environments and applications requiring real-time responsiveness. Emerging technologies such as mesh networking promise to extend seamless coverage across larger areas, eliminating dead zones in homes, offices, and public spaces. Integrated sensing capabilities may soon allow networks to detect movement, monitor occupancy, or even enhance security, all without additional hardware. The expansion of available spectrum, particularly in the 6 GHz and 7 GHz bands, will help alleviate congestion and unlock new possibilities for device manufacturers and service providers. Meanwhile, advances in artificial intelligence and machine learning are beginning to shape the management of Wi-Fi networks. Smart algorithms can optimize channel selection, balance loads, and detect intrusions in real time, making networks more resilient and efficient. Further on the horizon, researchers are already imagining what Wi-Fi 8 and even 6G wireless technologies might bring. While details remain speculative, evidence suggests that future standards will build on the strengths of current Wi-Fi, integrating even higher capacities, lower power consumption, and greater adaptability. The line between Wi-Fi and other forms of wireless networking could blur as devices move seamlessly between networks, guided by intelligent software. As Wi-Fi continues to evolve, cybersecurity will remain paramount. With so much of daily life resting on wireless networks, protecting data, privacy, and critical infrastructure will require constant vigilance and innovation. Collaboration among device makers, network operators, policymakers, and users will be essential to address emerging threats and ensure that the benefits of Wi-Fi are broadly shared. Across all these developments, one thread runs clear. Wi-Fi has become a cornerstone of modern society, shaping not only how we connect, but who gets to participate in the digital world. Its reach extends from the most personal moments in our homes to the largest civic gatherings in our cities, from the economic engines of commerce to the collaborative spaces of education and community life. The challenges are real: interference, security, equity, and more, but so too are the opportunities. With each new generation of technology, Wi-Fi draws us closer, making the invisible bonds of digital connection ever stronger and more inclusive. As we look ahead, the future of Wi-Fi is not merely a question of faster speeds or greater coverage, but of continued transformation of lives, communities, and societies. Its promise lies not just in the technology itself, but in what it enables: opportunity, creativity, and connection for all.